Is my screen visible to all?
Yes, sir.
Can you see my screen?
Yes, sir.
Okay. So today we will start a steam power cycle, that is a Rankine cycle. Steam power, or you can say that vapor cycle. Okay, Rankine cycle, which we call later. So can any one of you can differentiate what is the difference between a gas turbine cycle and a Rankine cycle? Major difference.
Rankine cycle consists of operates for two-phase material.
Rankine cycle works on steam, whereas gas turbine cycle works on combustion of gases.
Yeah, it is right. The major difference is the working fluid. Okay, for gas turbine, it is gas. For Rankine cycle, it is vapor. Okay, or steam, you can say. So the major difference between these two is the working fluid only. Okay. So can you tell any one of you can tell me what why we are using steam or vapor instead of gas? Although gas is readily available.
Compression of gas required lot of power input.
No, I'll give you some.
Because of water has the high specific heat compared to the air sun. So more heat is gained.
The major reason for using vapor or water, water is only converted into vapor, na? So it is the because water is chemically stable. First reason is that. Second one is that water is harmless. Like in gas, there are a lot of gas, argon, and all those. So that can react in the case of while transferring heat. Okay, with the so that can combust. That can create a lot of that problem. But in case of water is a harmless substance. Third advantage is that water is readily available. Also, it is cheaper, economic. So these three are the reason why we are using reason for using water as working fluid. Don't be confused because water itself converting into steam. So you can write any. Okay. So first one is that chemically stable. Second reason is harmless. And third reason is cheaper and economic. Okay. Now we'll discuss some terminologies which we have not discussed in that gas turbine. Okay. Like related to Rankine cycle. Okay. First one is the specific steam consumption, that we SSC we used to denote it. So what is the specific steam consumption? it is basically defined as amount of steam which is consumed to produce 1 kilowatt of power output. So this is his definition. And what is the formula? You just remember this formula. There is nothing need to derivation. 3600 upon work net, and its unit is kg per kilowatt hour. Okay, just remember this, because many at times they directly ask in gate exam. In the numerical part we will discuss what is the specific steam consumption of this cycle. Like this they ask. So just remember the formula. There is no need to go for any derivation part, I think so, for this. Oh wait, I have. Okay, just remember this formula. And second one is the heat rate. Heat rate that we represent by HR. So it is defined as rate of heat required to produce 1 kilowatt of power output. Okay, so its formula is m dot into qs divided by m dot to work net. So m dot will cut it out each other. So net heat supplied upon work net. And what it is called? Can anyone tell? It is related to some terminologies. Work net upon heat addition. What we represent it as? Wait, I'll make.
Efficiency.
Yeah.
Efficiency.
So it is inversely proportional to efficiency. So heat rate is 1 upon eta. Okay. Or you can also write here as or efficiency is equals to 1 upon heat rate. Now we'll discuss the Carnot cycle. These two terminologies are only additional. Rest we have already discussed, like work ratio, back work ratio in the gas turbine cycle. Almost all are similar. What is back work ratio? Just just
One minus network.
back work ratio
Negative
is
y by 1.
1 minus WC upon W turbine. Okay, is it? No.
WC
Yeah,
by
yeah.
W.
WC by W, yeah. And work ratio is work ratio. We were writing is like this, and this are W. So it will be 1 minus WC upon WT. Okay. Now we'll discuss about the Carnot cycle. You have already know the Carnot cycle. Hello.
Ah, yes, sir.
So Carnot cycle consists of which processes?
Two isothermal and two reversible adiabatic process.
Yeah, he is right. On the graph we can plot it like this. Is it? This will be 1, 2, 3 and 4. This I'll write here directly. 1 to 2 will be what? 1 to 2 will be isentropic expansion. Because reversible adiabatic process, we know we called it as a isentropic, so we will directly write it is isentropic expansion process. Okay. From 2 to 3, it is isothermal heat rejection. Okay. From 3 to 4, it is isentropic compression. And from 4 to 1,
Isothermal heat addition.
yeah. I'm just glancing it because you have already know this in the Yasdeep has already taught you. It will represent all the process in the plot also, so that it may become easier for you. Suppose the process
Sir,
is,
1 minute previous slides.
wait, I'll show you. 1, 2, 3, 4. Actually, these are a straight line, but because so it is a turbine heat addition, that is work is done on the turbine side. Heat rejection takes place here. It is condenser. It is pump or compressor, you can say that. Compressor. Here heat addition will take place. And it is called as boiler. Okay. Temperature T2 equals to T3. This is temperature in tropical TS curve. Okay. S3 will be equal to S4 and S1 equal to S2. Here T1 is equals to T4. Is it okay?
Okay, sir.
Okay. So this T2 equal to T3, we can also call it T lower temperature and it has T higher temperature. Okay. So what will be the network output for this cycle? Turbine work minus compressor work. Okay. So can any one of you tell what is another difference between these vapor cycle and the gas cycle turbines which are working on gas turbine cycles and vapor cycles? The major another that difference is that in case of gas turbine, we know that compressor work is given by minus integration V dP. Is it? Hello?
Yes, sir. Yes, sir.
Yeah. So in case of gases, the value of Vg is very
More.
less, very less. No. It is very high. Okay, Vg. But in case of that vapor, integration V dP, here because in the compressor side, here we are dealing with the vapor form of gases. So it will represent Vf. So it is very less, very less. Therefore, what will happen? The compressor work will decrease in case of vapor cycle. Therefore, the net work of the vapor cycle, that is this. So it will become increase. Why it will increase? Because the compressor work decreases in case of steam cycle. Okay. Hello. Since this is less, so compressor work will decrease. Here
Yes, sir.
here compressor work will increase. In case of gas, wait, I'll write gas turbines. Here steam turbines. Okay, so turbine which is working on gas and turbine which is working on steam. So in that case, because of the compressor work here is less, so net work output improves. Now, can anyone tell the difference between the what are the actually drawbacks of the Carnot cycle? You have already discussed in you have already studied in your thermodynamics. So, can any one of you tell? Hello. Okay, I'll tell you then.
सर मतलब पॉइंट टू अचीव करना पॉसिबल नहीं है क्योंकि डबल फेज है ना तो
Yeah, here because it is a yeah, you are right in Carnot cycle. Here it is double phase. It is a combination of that water and vapor both. It is in case of steam and vapor both are here present. It is in two form. Here it is liquid. Here it is vapor, and here liquid plus vapor, and here it is vapor you in the phase diagram. So here it is in the combination of both liquid and vapor. Therefore, you can also write it as I have directly latent heat of fusion. So you can also write as LV. You can also represent here. Okay, it is in a biphase. That's why its efficiency is compressor work is lower. Hello.
Yes, sir.
Yes, sir.
Okay, so what are the drawbacks of the Carnot cycle? So first, do any one of you know the answer?
Isothermal process may not possible, sir, because of in boilers and condensers, the pressure drop will occur.
Wait, so first drawback is that from here you can see that in the turbine the vapor, the saturated vapor, it after expansion converts into a mixture of liquid and vapor. Okay, so the liquid,
सो टरबाइन
yeah, so it will create the chances of erosion in the turbine will increase at the exit. Okay, because turbine exit is a mixture of liquid plus vapor. So
सर एग्जिट नहीं इनलेट
no exit turbine here inlet is saturated vapor. It is completely vapor. You can see now from this cycle, Carnot cycle.
यस
At the exit, it is a combination of I have already mentioned here liquid plus vapor, liquid and vapor. This side vapor. Okay. So it is a combination of liquid plus vapor. So at the exit of the turbine, chances of the turbine blades erosion increases. Okay. First point is say this. Second point is that it is difficult to design a turbine. Difficult to design both turbine and compressor which can handle both mixture of liquid plus vapor. So at the exit we are getting liquid plus vapor. Similarly at the inlet of the compressor we have to compress liquid plus vapor into that liquid. This line is basically represent the saturated vapor line. Okay, so we have to compress it to saturated vapor. We have to completely remove the liquid, but it is very difficult to achieve. So it is very difficult to design both compressor and turbine which can handle both liquid plus vapor region. Okay. Now I'll give you one question. It is a relatively simple question, so you can answer easily. A Carnot cycle, numerical I am giving. Carnot cycle operates between a source. Here's Carnot vapor cycle. Okay, source temperature of 311 degrees Celsius and sink temperature of 32.88 degrees Celsius. So we have to determine first work ratio RW, second specific steam consumption, third one efficiency. The data I am writing for the gases: pressure, temperature, HF, Hg, SF, Sg. Ten megapascal. Temperature is 311 degrees Celsius. Here is 38 degrees Celsius. HF value is 07.56. All are in kilojoule per kg. Okay, these are in kilojoule per kg and these are in kilojoule per kg Kelvin. Okay, 137.88 here at G 2724.2 2561.42 3.6 0.6 4764 0.4764. Here it is 5.6141. Here it is 8.3951. Okay, can you determine? Hello. Hello.
Yes, sir.
Can
Yes.
you can you do or should I do it?
Sir, we can do.
Okay. I'll give you 5 minutes. Then we'll discuss this.
सर प्लीज एक बार डाटा दिखा दीजिए.
Yeah.
So is the efficiency is 47.62 percentage?
Yeah, it is almost 47. It is correct. You have got 46 point.
47.62.
Yeah, it's fine. It is almost 47. Yeah, correct. So what is the specific steam and what is the work ratio? Hello.
So work ratio is turbine work by compressor work.
Work ratio is one minus back work ratio actually. 1 minus back work ratio, and it is 1 minus compressor work upon turbine work.
Is it 0.619 work ratio?
Yeah, right. And what is the specific steam consumption?
Sir, is specific steam consumption 3600 by W net formula? Is it correct?
Yeah,
Is it 5.72?
yeah, it is right. So all three are,
5 or
yeah, 5.7, 7.5, 7.45, anything is correct.
नहीं वो मैं
5.715.
Yeah, it is right. They will give you a range. So if your answer will be in that range, na, it will be correct.
मेरा
They always give a range.
5.78 है.
So wait, I will tell you the. So the process will look like this. Okay, it is at this point only. Okay, 1, 2, 3, 4. Temperature higher and temperature level they have mentioned. What is the temperature higher? 311 degrees Celsius, and it is 32.88 degrees Celsius. So we will convert it first. T1 is equals to T4 is equals to T higher is equals to 273 plus 311. So what is the temperature?
584.
584 Kelvin. Similarly, T2 equals to T3 is equal to T lower is equals to,
305.88 Kelvin.
yeah, 305.88 Kelvin. So first we'll directly discuss the efficiency. Efficiency of Carnot cycle we all know, T higher 1 minus T higher upon T lower upon T higher. Is it? So we can directly write it. Carnot for Carnot cycle is this only. So what is the T lower? 305 1 minus 305.88 divided by 584. So after calculating you will get this. Okay, do you know this formula or Should I tell you this? Hello.
Yes, sir. No.
You know na, because Carnot cycle you have already discussed. That's why I haven't told you this formula. I have just mentioned it. Second one, what is the work ratio? It is 1 minus back work ratio, or 1 minus WC upon WT. Okay. So at point 1, it is saturated liquid. So H1 will be directly equal to Hg. Okay. At Hg at 10 megapascal pressure and 311 degrees Celsius. Okay. So what will the value of H1? It will be directly equal to 2724.2 kilojoule per kg. Similarly, S1 will be equal to Sg. Similarly, at 10 megapascal and 311 degrees Celsius. So what its value will be? 5.61141
641.
kilojoule per kg Kelvin. Okay, for point 2. How we can write for point 2? For point 2, we know that it is an isentropic process. So S1 is equals to S2. Is it okay? So we can write Sg1 is equals to, or directly we know that 5.6141, and it is a combination of it is a wet region. So what is the formula for wet region? So SF2 plus X
X2.
into SFG. Is it right? So we can directly write what is SF2. SF2 at a pressure, it is at point 2 is at a lower pressure of 5 megapascal. Okay. So we can directly write what is the SF2. It is 0.4764 plus, we don't know the dryness fraction. Okay. So first we will derive dryness fraction from here, and that we will use for the enthalpy calculation. Okay. So what is SFG? It is Sg minus Hf. Okay. So 5.6141 minus 0.4764 is equals to X into, what is the value of Sg? 8.3951 minus 0.4764. From here, what you will get the dryness fraction? 0.6488. Have you got that?
Yes,
Yes, sir.
X2 dryness fraction at 0.2. So from here we can find enthalpy at 0.2 as HF2 plus X2 into HFG2. Okay. So what HF2 value is 137.88 plus 0.6488 into HFG. It will be difference of Hg minus Hf. Okay. So what will be H2? 137.88 plus 0.6488 into 2561.42 minus 137.88. From here H2 what we will get? Directly I am writing the answer, 170.3 kilojoule per kg Kelvin. Okay. Similarly for 0.4, directly we can write for 0.4 it will be equals to HF4 at pressure 10 megabar pressure and 311 degrees Celsius. Okay. So what is the HF value? It is
07.
1, wait, it is wrong, 1407.56 kilojoule per kg. Now just we have to calculate the third point. So for this process S3 and S4, it is isentropic process, so we can directly S3 is equals to X4. Okay, so from here we will calculate value of, what is the value of S3? It will is equals to HSF at a pressure of 10 megapascal and 311 degrees Celsius is equals to, what is that? SF4, it will be SF4, oh, wait, what is the value of S3? S3 will be equal to SF, value of SF at a 10 megabar pressure and temperature 311 degrees Celsius. So it will be 3.3596 kilojoule per kg Kelvin. Similarly, now for 4.4, 4.4, oh, it is S4, 4.4 actually, 1, 2, 3, 4. For S3 we have to calculate, it will be equal to SF3 plus X into SHG3. Okay, so what will be equal to, this we have to calculate at a pressure of 5 megapascal and 32.88 degrees Celsius. So what will be the value of SF3 at a pressure of 5 megapascal? 0.4764 plus X into difference of SG3 minus SF3. 0.4764 is plus X into 8.3951 minus 0.4764. Now these two, because it is process 3 to 4 is isentropic compression. So S3 will be equal to S4. So we can directly write 64 plus X into 0.3951 minus 0.4674 is equals to 3.3596. From here, what we will get the value of X? Tell me.
0.364.
Yeah, it will X3. Therefore, we can directly calculate H3 is equals to HF3 plus X3 into HFG3. Should I write directly the answer? You can put the values directly. So what is the answer you get S3? Can anyone tell?
1019.
1019 kilojoule per kg. Now we have got the enthalpy of all the value. Now just we have to put. So what will be the back work ratio? It will work ratio 1 minus compressor work upon turbine work. So compressor work is, what is the compressor work? H4 minus H3, and turbine work is H1 minus H2. Just put the values and we will get the answer. What is the value of H4? 1407.56 minus, it is 1019. 1019 divided by, what is the value of 2724.2 minus 1710.3. After putting the value, we will get 0.618. Okay. Third part, specific fuel consumption they have had, that is 3600 upon network. Its unit is kg per kilowatt hour. So directly put the values. It is 3600 divided by turbine work minus compressor work. 3600 divided by, what is turbine work? 2724.2 minus 1710.3 minus, here it is minus So 1407.56 minus 1019. So from here what we will get 5.745 kg per kilowatt hour. Is it okay? Hello?
Yes, sir.
Yes, sir.
Okay. Uh, if anyone is having any problem on a pure substance, uh, then should I discuss that in enthalpy calculation and all those things, or should we directly start the that Rankine cycle? Because I have skipped that part because you have already studied it in thermodynamics.
Sir, which formulas, sir, in pure substance?
Like this only, there's how to calculate the enthalpy in wet region, like this like this enthalpy in wet region we calculated HF plus H into HFG. These formulas, these are for vapor cycles, na?
Yes, sir.
If you know that, then we can directly move. Wait, I'll discuss in a small. So
Yes.
okay. So in this temperature entropy curve. So in the wet region, we represent it in the form of a straight line. In case of vapor cycle, this pressure lines. Okay. So if it is point A, B, it is C, D, and E. So what will be the enthalpy at point B? First I'm calculating on the boundaries B, D. So what will be the enthalpy at B? It will be equal to the enthalpy of the saturated liquid,
Yes, sir.
because up to this point it represent what it represent, saturated liquid, this line.
Yes.
Okay. And from here to this line represents saturated vapor. Okay. And this in between this it represents liquid plus vapor, both form. Here before this it is liquid and after it is vapor. Okay. This liquid plus vapor region is also known as wet region. Okay. So at this point B is exactly on the saturated liquid line, so it will be exactly equal to HF. Okay. Similarly, enthalpy at point D, since it is directly situated on the saturated vapor line, so it will be represented by Hg. Okay. Saturated liquid is represented by F, and vapor is represented by G. Okay. Similarly, for a point in between the wet region, how we can calculate directly? Hg is equals to enthalpy of saturated vapor, Hb, plus X into HFG. So Hb plus X into what is HFG? It is Hg
Hg
minus
minus
HF. So Hb is directly HF, so we can write like this also. Okay. Similarly, for point E, how can we write? Because it is in superheated region. And this point A is in subcooled region. So for superheated region, how we can write?
Hg plus
Cp.
Cp delta T.
Yeah, Hg plus Cp of vapor into
T superheated minus T saturated.
upon T minus TD. Is it? It is vapor. And TE we know temperature, and TD also we know. So directly we can write. And here HD is also that D. That's why we are writing in this one.
Excuse me, sir.
Yeah.
Sir, for water vapor also we can assume this at as ideal gas.
No. Ideal gases are different, and vapor is different. Gas we have to discuss in the gas turbine cycle. Vapor we cannot assume as a CP for vapor. They will give that in the question. If someone will ask for the vapor reason.
Yes, sir. Sir, but actually the CP delta T is used for ideal gases only, so that's why.
No, it is also used for this also. CP for vapor we are using, not for the ideal gas. If they will ask in the question, they will mention this. Okay. So
Okay, sir.
don't worry about that. Now for that subcooled region, how we can write for the subcooled region? That is point A for HA. What will be the value of HA?
HB minus CP
Minus
delta T.
CP of, here we will use of CP of liquid. Okay. CP of liquid into TB minus TA. Okay. This you can use. Similarly, entropies we can write. This is enthalpies we have written. Similarly, entropies we can write. Entropy at point B will be is equal to SF. At D it will be equal to SG. At C it will be equals to what it will be equals to SB plus X into SG minus HF. So SB plus X into SG minus SB. Okay.
Sir, so this CP delta T is valid for any substance, so even incompressible, but the CP value alone changes like that.
Yeah.
Okay, sir.
CP value will change. Temperature del T will remain same. Only CP value will be different for ideal gases. It will be different. For vapors, it will be different.
Okay, sir.
Okay. Similarly, for point E, what will be the value of that? It is superheated region. So HD plus CP of vapor. Okay. Into
ln of
yeah log T.
TA by TD.
Yeah. And and for point A, it will be SB minus
CPA
CP of
liquid.
yeah CP of liquid into log TB upon TA. Okay. This only you have to remember for pure substances. That will be applicable in our this cycle formulas. Okay. So directly we will now go to Rankine cycle. So in the now, can anyone tell me what is the difference again? Difference between the Rankine cycle and Brayton cycle. I have already told you in the starting of the class.
Working.
Majorly working fluid.
Yeah, working fluid. So all the four process, that is okay. So only difference is working fluid. Here working fluid is vapor, or you can say that water is the working fluid which will be convert into vapor. All the process, that is first one is isentropic expansion. All the four process, that is expansion, heat addition will take place at constant pressure, all will be remaining the same in case of both the cycles. So 1 and 2 will be the, from 1 to 2 isentropic expansion will take place, from 2 to 3 constant pressure heat rejection will take place, from 3 to 4 isentropic compression, and from 4 to 1 constant pressure heat. You can also include 5 also, because 5 is also going for 5 heat addition. Okay, so only difference, that is working fluid is different. There we are using gas, here we are using water or vapor. Okay, so we have already discussed that the net work output of Rankine cycle is higher. Why it is higher? Because net work, we know that turbine work minus compressor work. So at the inlet of the compressor, it is WC is represented by WV into dP. So V here it is in the form of saturated liquid, and it is very very small. So compressor work decreases, net turbine work increases in case of the Rankine cycle compared to Brayton cycle. Because in Brayton cycle or gas turbine, that here minus dP, here it is of gas, and it is not negligible, it is very high. That's why compressor work is also high. Okay, hello.
Yes.
Yes, sir. Sir,
Yeah,
Can you repeat the points?
do you want to write?
can we operate? Sir, can we operate the reversed?
Kya?
Can we operate the Rankine vapor cycle with a superheated region?
You are
With
not,
superheated.
your voice is not clear.
Can we operate the Rankine cycle with superheated steam, sir?
Yeah, we can use superheated steam also, but for the simplification, I have just drawn it for the simplification. You can also start it from here, superheated region also. There is no problem.
But sensible heating when takes place, sir.
Yeah,
When we operate the superheated region, the point one to two.
yeah. That it is not necessary that point 2 will always be in wet region. it can be on this line also, it can be in superheated region also. That will depend upon the kind of the steam which is entering into the turbine. Okay,
Okay, sir.
that we cannot directly since we are for representation point of view, we are starting the heat in the form of saturated vapor region. That's why it is coming in wet region, because 1 to 2 process is isentropic process. Okay, so entropy will
Okay,
remain same.
okay.
That's why it is coming in the wet region. If suppose the steam is in superheated region like point here, okay, so in that case it can come here anyway point, it can stop here or it can stop here. Okay, so that we have to calculate that they will give pressure in the form of pressure, at what pressure it will stop. Okay, in the question they will mention each and everything. Hello.
So,
Okay.
sir, can you kindly repeat this point regarding the uh, pump and compressor inputs?
Yeah, that I will discuss now.
Okay. Sir.
Now for the process 1 to 2, it is isentropic expansion that is to take place in the turbine. Okay, so what will the turbine work? Turbine work will be H1 minus H2. So now for process 2 to 3, it will be condenser. Here what will a constant pressure heat rejection will take place. Okay, why I have mentioned this straight line? I have already told that in the wet region the constant pressure line are represented by straight lines. Okay, that's why I have mentioned. But here in that just left or right of that this line, saturated liquid and vapor line, the pressure lines are in the form of curves. Okay, so if it is this is same pressure, don't you get this pressure is same. Okay, only the method of representing that in the wet region is a straight line. That's why I have mentioned it is straight. Well, otherwise the pressure for 451 it is same. Okay, so for the condenser heat is rejecting, so it will qc qr, you can say that qr. What will be the qr? It will be h2 minus h3. Similarly, now for 3 to 4, it will be pump isentropic compression, or inside the pump it will take place. So what will happen? H4 minus enthalpy will increase. H4 minus enthalpy for the pump will be like this. Also here, because pump as I have already discussed, integration minus dp is there, so we can represent directly like this: p higher minus, after integrating, p lower. Okay, so we can also write like this for this if you are not given the values. Okay, for process 451, it is boiler. Directly writing P equals to C, heat addition, constant pressure heat addition will take place, and Q supplied. What will be the Q supplied? H1 minus H4. So anyone was having doubt in this? Hello.
No,
Yes, sir.
sir.
Hello.
No, sir.
Sir, I was actually asking about the compressor and pump work inputs, which you mentioned previously. That ones.
Yeah. So what is the problem you are facing?
No, sir. I just wanted you to repeat this point so that I become clear.
Okay. The difference I was here discussing about the difference between the Rankine cycle and the Brayton cycle. For the Rankine cycle, actually, since liquid is entering in the form of saturated liquid form at 0.3, okay, in the pump. So the pump work, or you can say the compression, WC or WP, you can say that it will be minus integration VdP. So here the value of that specific volume, or you can say that VF, it is in the form of saturated liquid. So its value is very very less, as we have discussed in this numerical also. From here you can say that at the here actually they have not given, but in actual its value is very very less for vapors. Saturated liquid, it is very very less. Therefore in case of Rankine cycle, the compressor or pump work decreases compared to turbine work. That's why the net work output increases for the Rankine cycle, okay. But in case of Brayton cycle, since the Vg, that is a specific volume for the gases, is not negligible, it is very high compared to vapor. So the compressor work there, it is higher, and in that case that work net work output is reduced. Hello.
Yes, got it.
Okay.
Thank you.
Okay. So can any one of you tell that which of the two cycle I have discussed? Carnot cycle na, and Rankine cycle, both are vapor cycle. Carnot vapor cycle and Rankine cycle. So according to you, which one is having the higher efficiency?
Carnot cycles.
Carnot cycle.
Why it is having higher efficiency?
Because it is the ideal cycle.
Yeah, ideal cycle, but there may be some reason na?
Yeah, constant temperature process, sir.
The main reason is that the mean temperature of heat addition, okay, in case of Carnot cycle, it is higher compared to Rankine cycle. That's why. Wait, I'll show you both the process on the same diagram first. Okay. One, two, three, 4, 5. Okay. If we will draw dash dash line here, 5 dash, then this 1, 2, 5 dash 5, it will represent Carnot cycle. Okay. Hello. And 1, 2, 3, 4, 5, 1, it will represent Rankine cycle. Okay. Hello.
Yes.
Okay.
Yes, sir.
So what is the efficiency? Efficiency, it is 1 minus Q rejected upon Q supplied. Can we write like that? It is the formula na? There are many forms of writing. That is work net upon heat supplied. Okay. Or we can write that Q net upon Q not 1 minus Q rejected upon Q supplied. These are different form by which we can represent the efficiency. Okay. So we are using this one, 1 minus Q rejected upon Q supplied. Okay. So what will be how we can write Q rejected? We know that entropy we know that del Q upon T. Can we write like this? Because
Yes, sir.
from entropy is del Q upon del T. From thermodynamics you have studies in the entropy section you have already studied. So can we write del Q by T into del S, Q T into del S. So Q rejected, can we write like that? Q rejected T lower into del S Similarly, Q supplied can be write T higher into del S. Okay, so efficiency, how will change now? T lower into del S, T higher into del S. Okay, this is the derivation of the Carnot cycle. 1 minus T lower upon T higher. Okay, this we can write. Hello.
Yes, sir.
Okay, so now we will draw again that same curve. Okay, 1, 2, 3, 4, 5. So the temperature which is required at which temperature it's heat is added in the boiler, so in which it is higher, Carnot cycle, this one Carnot cycle, or in Rankine cycle, this cycle.
Car- Carnot cycles.
Carnot.
Yeah, because at in Carnot cycle the temperature at which mean temperature or heat addition, you can say that it is higher in case of Carnot cycle. What is mean temperature? T1 plus T5 divided by 2. Okay, so here in case of Carnot cycle, at temperature at which heat is added, it is higher, it is T5, directly it is Th is equals to T5. But in case of Rankine cycle, where it is T4. Okay, Carnot cycle, Rankine cycle.
Sir, is efficiency for Carnot is even higher than the reheat and regeneration cycle? A superheat and reheat cycle?
That we'll
Rankine.
discuss later. First, we are only discussing in terms of the general Rankine cycle. Okay, so in that case, 1 minus it will so since T higher for Carnot cycle is higher, so what will happen? Efficiency for Carnot cycle will be higher than Rankine cycle. Okay, hello. Or you can also understand in this term also, mean temperature of heat addition term also. So efficiency, how we can write? It is 1 minus T mean temperature of heat rejection into del S, or mean temperature of heat addition into del S. Okay, so mean temperature of heat rejection for both the processes almost same. Okay, so mean temperature of heat rejection, it is same, that is almost same, because it is 0.35 and 0.5 dash, both are almost nearer to each other in that case, so it is almost same for both the process. So what will happen? So it will directly write like this, and mean temperature of heat addition into del S. Okay, so mean temperature of heat addition, so it will be higher for Carnot cycle, it will be 5 T5 plus T1 by 2 for Carnot cycle, whereas for Rankine cycle it will be T4 plus T1 by 2. So if both this statement also comes, you can mark it as a it is a correct term. So so efficiency, normally they ask in this terms, this form only, that efficiency of Carnot cycle is higher than Rankine cycle. Reason they ask, they will give 3 or 4 hours question, 2, 3, 4. First they can ask uh, mean temperature, because work net is higher. Second, they can give heat supplied is lower. Like this they can give, and one they will give mean temperature of heat radiation is higher, or none of these. So in that case, like this they can give example options, and after then you have to mark one of them. Okay, so they can ask this question in 1 marks type question, that efficiency of Carnot cycle is higher than Rankine cycle. Why it is higher? The mean temperature of heat addition is higher for Carnot cycle. Okay, you have to mark this.
Sir,
Yeah,
isn't it true that the area enclosed by
yeah,
the
yeah. That also,
Rankine cycle is small?
but they will know, they won't ask this in the gate exam. They will this they can ask in the engineering services type of exam. That area
But
enclosed.
actually, not regarding this question. Like generally, I'm asking if we have the area under 1, 2, 3, 4, 5,
Yeah,
like
yeah,
on the TS diagram,
yeah,
we can find that the area is more. No? So like, so won't the work net will be more?
yeah. The network output. What you are asking about in that area?
So if the area is more, like usually the efficiency will be more.
No, area under that curve, basically what it represent, it is used to represent the network output. Okay,
Yes.
so area basically of that curve represent how much work is being done. It won't represent the efficiency of the cycle. For work done we can represent that area, but for efficiency we have to calculate the mean temperature of heat addition. Hello.
Okay. So the efficiency doesn't depend on the area under the curve.
No, it that area basically uh,
डिपेंड करती है यार.
hello.
सर डिपेंड तो करेगी ना,
uh,
बिकॉज हमने वो टेम्परेचर ऑफ हीट एडिशन की बात कर रहे हैं, तो इंटीग्रेशन ऑफ होल दैट लाइन उसी को तो करेंगे तभी तो आएगा.
uh,
क्यू इक्वल टू टीडीएस होता है.
okay, that I will discuss in the next class. That part first I have to also read that part also, because I don't remember that part. So I will study, and then I will discuss in the next class that part. Okay. Hello.
Okay. Sir.
Okay. So
Yes.
today,
Yes.
what is the time right now? Okay, so we'll stop here only today, because it is already 7:19. So in the next class we'll discuss that part. Okay, because I have to also study that
ओके.
part. I don't know that part. Hello. Hello.
Yes, sir. Okay, sir.
ओके.
Okay,
So no
then
problem, sir. We can discuss.
we'll discuss that part in the next class, and next class we will start some numerical and that part. Okay, we'll discuss some gate problems in the next class, because today actually I prepared that sheet, but I'm not finding that sheet in which I have written all the questions of the previous year. So
Sir,
actually,
we can wait for some minutes.
do you want to discuss that problem today only?
No, means whatever numericals you are going to take.
Yeah, that's what I'm saying. That actually I was about to discuss some numericals today, but the sheet which I was having, I am not finding that today. So we will discuss problems in the next class. Okay.
Directly on Wednesday, sir.
Yeah, in that class we will discuss. First, we will discuss the that performance parameters, and then we'll discuss all the numericals. Okay. So from this chapter, that Rankine cycle, definitely you will get a question in the GATE exam. In suppose there are two morning and afternoon session. Na? In every session you will find a problem regarding this, because from the every year they are asking a question for 2 marks, 2 to 4 marks they are asking in every paper. So last year also they asked both the sets. They asked 3 marks questions from this topic. Okay, so we'll discuss numerical in the next class, and because I'm not having that sheet, I'm searching but not finding it. Okay, we'll discuss in the next class.
Sir, where is the link of recorded lectures, previous lectures?
I have shared you the channel na. Wait,
Yeah, can you just share because
wait, I'm sharing.
I didn't get it.
So the next class is on which day, sir?
Wednesday only. Wait, I'll share you that channel link.
Is it channel link?
Yeah.
Where is the link? I didn't get
Wait.
it.
Okay.
I have shared. Are you talking about the channel link?
Yeah, this is the. You can find all the lectures there. Today's lecture also I will upload there only. Hello.
So the next class is on Wednesday itself, sir.
Yeah, Wednesday itself. So in the from the
Thank you, sir.
next class I will try to solve as many questions as possible. So I think for 40 to 50 questions are there, I think, total, which they have asked in the previous years. So we'll try to solve most of them in the class itself. Okay, whether it will take 2 class, 3 class, it won't matter. We'll try to solve in the class itself. Okay.
Okay, sir.
Okay. So
Okay.
Okay.
okay, we'll stop the class here only.
Thank you, sir.
So thank
Thank you,
you.
sir.
And that part I'll discuss in the next class. That area under the curve. Okay.
I think. Can I talk about it first? I think because of heat input is also increasing, maybe it is counterbalanced because of that.
Yeah, that I have to study
If
because I have prepared the note
I think so,
directly.
right? Even I'm not.
Hello.
Sir?
Yeah, because the notes which I have prepared now, I haven't mentioned in that. So first I have to study in the books, and then only I can tell you regarding that.
Okay, sir.
Yeah.